పేపర్ తీసుకుంటాను. పేపర్స్ అసలు గౌరవ తనకు జాబ్ రాస్తారు కదా, అందులో
Hi Sanjay, how are you? Am I audible? Okay. You can just unmute and talk. We are only two here. So you were present in last class, right? Where we did the simulation. Were you there? Right. So you have the Aspen file now, wherever we stopped last week. Okay. We'll continue with that Aspen file. Okay. Just keep it open. Meanwhile, I'll wait for some more time. Let's see if others are joining this class. Just keep that Aspen file ready. Keep it open. We'll continue further. Okay, fine. Now we'll just get started. I think we have waited enough. Hello, Mr. Sujo. How are you? Sijosu Kumaran. Am I pronouncing your name properly? Yeah, can you just tell me once again? I was mute.
Am I audible, sir?
Yeah, now you're audible.
Okay.
Okay. Is this your first class or have you been before?
Now, I've been before.
Okay, fine. Which week were you there? Can I just recollect?
Last week.
Okay, last week you were there. Fine, great. So last week, could you do the Aspen thing, whichever we discussed in the class, or you still have thing to do?
Yeah, actually, I actually done that, sir.
Okay, you have done the simulation part, right?
Yeah, I'm actually doing that parallelly.
Okay, you're doing parallelly, fine. Uh, so you have that simulation with you now, do you?
What's our last class simulation?
Yes, last class simulation, whatever the liquefaction cycle we have simulated.
No, I actually didn't save that.
Okay, fine. But you told you were doing it parallelly, right? So which one you're
Yeah.
talking of?
Hello.
Yeah, see, you told that you are doing parallelly, right? So last week we have simulated a liquefaction cycle, but you said you couldn't see that, so I mean, kind of contradictory statements.
No, no, not save. I didn't save that. Save.
Oh, acha, you didn't save that. Okay, sorry.
Yeah.
Sorry. Okay, fine. No issues. Sachin, what about you? Do you have the file? I'm asking this question so that I want to continue from the point where we left. That's why I'm asking this question. Sachin, am I audible, Sachin? Sachin, any response? Okay, let's got something. Let me share this. Okay, just meanwhile, I have only few questions. Okay, after that, we'll continue on optimization and the sensitivity analysis for today's session. So, yeah, so let's get started. These are the few basic processes which Professor discussed. So, can you just answer this question? Which of the following are the standard reactor blocks available in Aspen? IKMR, Staikivari, Queen, or Crystal? See, meanwhile, you just keep your Aspen ready, okay? Sachin left the meeting, is it? Okay. It's just straightforward answer, right? You have stoichiometry based on equilibrium based reactors. Fine. So this question is relevant to the figure 1, which is shown over here. See, do you see this? You have a CSTR. It has got certain input. Uh, the labeling is over here. Okay. What all the values given? So now I want you to answer what are the valid phases given at the input C. Which valid phases will you give in this system by seeing this figure? What about Sijo? What do you think is the answer? Sanjay, can you explain why you are calling it as a vapor phase?
Sir, because it is a dryness function of one.
It has got the molar vapor fraction as one, right? As at the input, at the output as well. Since you have both vapor phases at inlet and outlet, most likely that the reaction is happening in vapor phase. So, can I have a situation where my inlet is vapor phase, my outlet is vapor phase, however, my intermediate thing can be in liquid phase? Sanjay, guess you are the only person in the meeting.
Sir, can you repeat the question again, sir?
Inlet will be in vapor phase, outlet will be in vapor phase. However, the intermediate thing can be in two phase. Can we have such a situation?
Yeah, I think it may be possible, sir.
Maybe possible, right? Yeah. So what do you do in that in such case?
I have to give both vapor and liquid,
Yeah,
and
so although the question is asked only for vapor phases example, but it will be good if we can give both, because we don't know what is going to happen intermediately, right? Yeah, fine. The same thing. Okay, so we were simulating this process in parts. So we'll continue where we stopped. Okay, so previous week I asked I asked this question, asked you to simulate this particular process given the cold box, the red box thing, with the given inputs, right? So I am assuming all three of you in the class were able to simulate this process, right? Sanjay, you told you were able to do. Sachin, were you able to do this simulation? Sachin, am I audible? Okay, done, right? So do you have Aspen file now? Can we continue further for optimization? Three of you have. Sija, can you just try to simulate the process? Uh, just take a screenshot of this. Try to set up the flow sheet and just do the simulation, and we'll just go forward for the optimization meanwhile. Okay, just take a screenshot of this, or I have shared this PPT in last week itself. Okay, so you can download it from there on. Okay, so we'll continue with the optimization. Okay, so now in addition to this, see, we discussed about the exergy efficiency, right? And we have put a calculator block for calculating the exergy efficiency. If I remember, it's about some 40%, which we got. I don't remember the exact value. Now we want to maximize the efficiency of the particular process. Okay, so for that we'll use optimization. Okay, so now in this case, the question asked is maximize the exergy efficiency of the process. You have three variables: temperature of steam 4, temperature of steam 5, and the split fraction, whatever you are the fraction of 4 that you are passing through the expander. Okay, what are the constraints? You have a temperature minimum temperature approach of heat exchanger 1, minimum temperature approach of heat exchanger 2 should have certain value. It should be at least greater than 5, and this is one condition. What is minimum temperature approach in a heat exchanger? What is the minimum temperature approach in a heat exchanger? Anyone? Three of you? What about other two? Sanjay says it's difference between hot and cold. That's I'm asking minimum temperature approach, not just the difference at every point. I'm asking you what is the minimum temperature approach. Okay, fine. Uh, See, you must have studied in a heat transfer course where heat transfer only occurs when you have temperature difference, right? So, in a heat exchanger, the heat transfers from hot steam to cold stream, right? So, now at every location along the heat duty axis, the difference between the temperature of hot and cold streams is calculated. Okay, so since we know the difference, a minimum of the minimum of the difference curve is calculated. The minimum of the difference curve is called as minimum temperature approach. Okay, so why it is important in heat exchangers? Because when you have lower temperature approach, you'll have higher there's a need of higher heat transfer area. Okay. And you can't have negative minimum temperature approach. Okay. And you can't have like a zero value. If you have a zero temperature approach, which means you require infinite area for that heat transfer to happen. Okay. So according to the commercial variable thing, the minimum temperature approach value is given. Okay. So in this case we assume the minimum temperature approach in both the heat exchangers should at least be greater than 5 Kelvin. Okay. That's one of the constraints which we are posing on the problem. And what is the other constraint? Single phase in the expander. The expander means this one. Okay. What is the need of having single phase in this expander? Can anyone explain? Why do we need a single phase in that expander? Yes, the pinch point and the minimum temperature approach are the same, correct. What is an, I asked you one more question. There's another constraint called a single phase in the expander, right? Why do we need single phase in the expander in this? What is the need for having a single phase in expander? What do you think? Yes? Any answer? You can just guess it here. See, this is kind of an informal meeting, okay? So, you can just talk. Have you heard of erosion? What is expander? It's the continuous rotating blades. Okay, it's just like your fan. So in your home, to the fan, if you just continuously pour water or something of liquids, what would happen? Slowly it will erode, right? However, it will work fine as long as it pumps the air, correct? However, if you just put some liquid on it, slowly it will start damaging, right? So in this, which even in this case, if you have very high velocities, the erosion is quite uh, the probability of the expander getting eroded is very high. Okay, so you'll have mechanical failures. Okay, that's why we'll put a constraint saying this expander is single phase. However, this expander can have two phase because this is a cryogenic turbine. Okay, cryogenic turbines are employed specifically for expanding the two phase thing. Okay, two phase input. So what are the constants do we have? The pressure of the stream 3 is assumed to be 40, and the temperature of stream 3 is assumed to be 300, and pressure of stream 6 is assumed to be 1. Okay, and isentropic efficiency of expander is 85%, and similarly for cryogenic turbine is 70%. Okay, can you try setting up this? You have an objective function of exergy efficiency which we have defined last week, right? So use the same file. Okay, open that file. You have objective function as exergy efficiency, you have these three variables. Okay, and constraints as your minimum temperature approach in heat exchangers 1 and 2, which is greater than 5. You have a single phase in expander, and constraints P3, sorry, constants. Can you try setting up the flow sheet and then the optimization? In case if uh, Okay, to Sanjay, it's clear. What about Sachin and Srija? Could you get the question? Sachin? Yes, Sachin. Start doing optimization. Srija, what about you? If you have previous week's file, start doing the optimization. Okay, if you don't have the previous week's optimization file, then try doing simulation first and then optimization. So in case if you have any doubts in between, just let me know. Okay, you can either talk or just put it in chat box. Meanwhile, I'll be posting this. Okay. Hi Ganeshit. Did I pronounce your name properly? See, you must have given a calculator block, right? Last week. Do you have that? So this is the file which we used last week. Okay. you have this, right, in the calculator block. You called the exergy efficiency to be export variable and a parameter number to be 1, right? So use the same thing in the optimization also. Once you go to optimization, the definition, use it as model utility and give the same parameter number whatever you have specified in the calculator block. Okay, that's how you define it. Use the same name and same parameter number. Keep posting your status here. Can you update me about your status, guys? Okay, please continue. Guys, can you tell me your status? Where are you? Sanjay, Sachin. Variable tab. Okay. Continue. See, with maximize and minimize, Sachin, it's asking you whether you want to maximize your objective function or minimize your objective function. Okay, that's what it means. So since what to vary, so you have the variables over here, right? Temperature of stream 5, temperature of stream 4, and then you have a split fraction, right? What fraction of stream 4 should go to expander and to heat exchanger. Okay, limits. You know, see, in real world, we actually don't know the limits. Okay, we put our limits based on the physical constraints which we have. For example, if I had to give you a simple example, the split fraction, since we are talking of fraction, it can't be less than 0 and more than 1, right? So we'll give lower limit to be some, let's say 0.01, and upper limit to be 0.99, something like that. So depending on the physical constraints, we give the limits. Okay, and similarly for the temperature. So here we said no, okay, can you answer what should be the limits for temperature? See, I explained for the split fraction, right? Similarly, using the physical physics of the problem, can you explain what could be the limits for the temperatures at state 4, at state 5? This at state 5, something like that, Yeah, correct. Since we are talking of a cryogenic expander, so it can't be more than 123 kelvin. So, kind of that's how you define your limits. Okay, they need not be very strong. You can change those limits also later on. For the first iteration, you just go with the physics of the problem. Okay, that's how you try setting up the limits. Okay. You just check the value which we gave initially for the temperature of steam 4 and steam 5. uh, in particular region of plus minus 20 kelvin, it could be your range. Okay, so that's how you define. Let's say if you have given steam 5 temperature to be 100 kelvin, then your range can be some, let's say, somewhere around 80 to 120, something like that. A split fraction is a block variable. Okay, since we are using a splitter for, sorry, I was talking when the mic was off. See, split fraction, since we are using the splitter block for splitting the input stream, so it becomes a block variable. Okay. Why do you want to do a dynamic simulation? Who is this, Sanjay? You're doing a dynamic link. Why do you want to do a dynamic simulation? Do a steady state simulation. You're trying to do dynamic simulation. Check Sanjay. Sorry, Sanjay. We are just doing a steady state optimization. Okay, no more than that. I'll just answer your question, Sanjay, because I don't know where are you, right? So, with respect to Sachin's question, see, it can be either, okay? You can either vary for A or for B. See, one is X and one becomes 1 minus X. So, you can either vary for A or for B from 1% to 99%, either way should work. Or in case whatever you have given input, just check your simulation input for whatever stream you have specified the fraction, give the same string value in the variable. Okay. Sanjay, is it possible for you to share your screen? I'll stop the presentation. See, you went to dynamic configuration. You don't have to go there. Just
Sir, how to turn it off? That's
just go there, uh, click on, have a right click, go to dynamic configuration, right click. Uh, it's not getting. Go click on dynamic options. This is dynamic configuration or dynamic options. Right click. Yeah, just delete. Yeah. Doesn't come anything, is it? No, just reset your thing first. Save your file. No, it's already open with the Dynamics. And what did you do to get into Dynamics? Can you show me the optimization? O1. Okay. Objective constraint, maximum sexual efficiency C1, C2. Don't put 0, write some 0.1. Not that, the split fraction, third one. Let's say 0.1 to 0.9. Just save it and run. Let us see what happens. Save the file first. What is this here? Server couldn't restore one subroutine, COpt is missing. You have installed the optimization package, right? Oh, Sachin, you also have the same value. Okay. You do one thing. Sanjay, just stop presentation. Let me try doing it. If I also have the same problem, then there is some issue with question itself. Okay. Let us see what happens. I'll try solving. This is how we define parameter, but before defining the parameter we can give the constraints. Okay, so we'll say total we have 3 constraints, right? So I'll say this is meta 1, meta block variable, which block, it's a block is hx1, right? Meta, next specify meta should be greater than or equal to 5. Let us give tolerance as 0.01. Okay, this is first constraint. We have second constraint, meta 2, meta block variable hx2, meta, let us specify this, meta is greater than 5, 0.01. These are the two constraints. We have one more constraint in the question which says it should be the single phase expander, right? So for that, what will we do? We'll say the stream 9 should be the temperature of stream 9 should be greater than its dew point. Okay, if we are talking of temperature greater than its dew point, then definitely we are in vapor phase, right? So this is stream 9 T9 dew. We need to define 2. This is stream variable, stream number 9, this is temperature, this is T2, this is stream 1, this is stream property, right? Since we are calculating dew point, so it becomes property, so we need to put stream property. So we don't have stream properties here, we need to define properties. Go to properties, okay, we'll define it other way. Let me delete this. Let's say if we want to analyze generic thing. How do we define? This is just a dummy thing, okay? This is dew point temperature. Okay. Just I have created a dummy T dew so that I'll be able to calculate the dew point temperature there. Okay. See, I have T dew. Let us put in Kelvin so that we don't have any confusion. So we want T9 minus T9 dew should be greater than at least some certain 2 Kelvin. Okay. 0.1 is my tolerance. Fine. So these are the three constants which we have. So here we have defined the objective function exef, right? Exef. Spelling should be proper. Exef, sorry. We have all active constants. Is this? Now here we have three variables. So the first one is what are the three variables do we have? It's the stream 4 temperature, stream 5 temperature, and the split. So I'll define the stream 4 temperature as a block variable because we have defined the outlet temperature of the heat exchanger, right, which becomes the stream 4 temperature. So let us define this as a block variable instead of defining it as a stream variable. So now block 1, this is hx1, which is this is a hot outlet temperature, right? Let me put it in Kelvin. What was the value which we gave? Previously we gave 225 Kelvin. So let me give a lower value to be 200 and upper value to be 250. And similarly, the steam, the other steam also is hx2. This is hot outlet temperature. Stream B. It's in Kelvin. What is the value which we gave? We gave it to be 127 Kelvin, right? So it is 127 Kelvin. Let me write 100 Kelvin to 150 Kelvin. And third one is a block variable of the splitter, right? So fraction. Before giving here, just go to split and make sure that you are given to the same thing. We gave to 4b. We'll give it to 4b. Okay. The lower limit is 0.1, upper limit is 0.9, right? So all the required inputs are given. Let me just reinitialize this net. Let us see what happens. Yeah, see, I have some answer with the warnings, so which is fine. Constants are not satisfied, but fine, it's running properly. At least didn't have issue with whatever you were saying. I guess you have done something different. Did you people do something different from what I did? Sachin and Sanjay? Oh, totally. Okay. So this is how you are expected to do, okay, the optimization study. In constraints, okay. So now it is clear, right? How do we define constraints and all? Okay, Sanjay. Okay, to Sanjay, you are clear with what we are supposed to do? Okay, great. Now can you try simulating it and tell me the optimized value, both of you? I'll show the question once again. Let's try solving it and let me know the optimized value. Can you tell me your status, guys? Sanjay and Sachin. Constraints, okay. It's the hot outlet temperature, right? See, in the heat exchanger, both the HX1 and HX2, you are wearing the hot outlet temperature. So it becomes hot outlet. Yeah, I'll show you. See, I don't have this charger, okay, so we'll have to be a bit quicker. My laptop has gone already into power saving mode. Yes, Ganesh.
Sorry, sir, actually, I'm late हो गया था. मैंने response दिया बीच में.
Sorry, I can't hear you. Your voice is a bit unclear.
सर मैं लेट हो गया था थोड़ा क्लास को, इसलिए मैंने बीच में रिस्पॉन्स नहीं दिया था. बस कॉलेज से आया था साइड से.
No, you're talking in Hindi, is it? Okay, okay. Couldn't follow. Can you just repeat?
Sir, I was late for the class. That's why I was not responding in the middle of the class.
No,
And because I don't know what is the question going on exactly, that's why I didn't respond in between.
you joined this class in between. That's what you want to tell.
Yes, and I didn't follow the question, and that's why I didn't answer.
No issues. That's okay. Now this is getting recorded. Okay, I'll upload this video on YouTube and I'll share the link also. So if you want to continue with these sessions, you can join next week till wherever we have stopped. From that point on, we'll continue in the coming lecture. Okay.
Okay, sir.
Okay. Yeah.
Then I have actually doubt also. It's related to assignment also, sir.
You're a?
Sir, I have doubt
Okay. What is that?
related to assignment.
Which assignment?
Sir, the recent assignment of week that tomorrow, week 9.
With assignment 9, is it? You still have the submission line, right? I mean, it's tomorrow, so
Yes, sir.
I won't be able to discuss it today, Mr. Ganesh. If you have submission date tomorrow.
Yes, actually, sir, I have a doubt about the how we are supposed to solve if we are not given the distillation rate or reflux rate of the distillation 1 as
No,
option 1.
Okay, I didn't see the question. Okay, so I won't be able to connect to whatever you're asking. This is about distillation absorption, is it? But I'll go through it and come back to you. Because, however, I won't be able to discuss it today because you still have time to solve, right?
Okay, sir. Sir, but sir, the absorption and
If you think the
absorption
question
distillation,
itself
how
is
it will be different?
that's what, if you think the question is incomplete, you still require some more information, then you can just put a mail in the mail ID given in the website. Okay, because I'm not the one who is preparing those assignments, so I don't know what is given and what is not there. So uh, yes.
Okay, sir.
Yeah.
Thank you, sir.
Okay. Okay, Sachin and Sanjay, you are able to finish the problem. Okay, fine, Sanjay. Sachin, what about you? Sachin, can you please respond? Okay, see, the variables, whatever inputs you have given. Okay, for example, the heat exchanger input, we specified hot outlet temperature, right? So you can only vary the hot outlet temperature of that particular heat exchanger. And similarly, the split fraction in the split clock, whatever you have varied, the same stream you can vary. Okay, you can't vary any other stream. So I have given 4b. That these are the only considerations which are supposed to take, nothing else. So any other question do you have with respect to today's class?
Sir,
Yes.
sir,
Yes,
sir,
Francis.
we have the recorded videos uploaded.
Yes, all the recorded sessions are uploaded.
Sir, where I
Where?
I didn't
Okay,
able to find any session.
in the Swayam website, when you open Aspen, uh, on the left side you have problem solving sessions, right? uh, Left side there's a tab called problem solving. Just click on that, you'll be able to open an Excel sheet, spreadsheet. There you will be able to see all the links.
Okay, sir.
Okay.
Okay, sir.
Yeah.
Thank you, sir.
Fine. Sachin, you had some doubt? Okay, fine, you can share your screen. I'll stop presentation, but be quick, huh? See, I don't have my laptop charger. That's my main worry.
Hello.
Yes, Sachin.
Sir, problem statement was given to enter the liquid or a vapor mole flow. So which flow should we enter? So the liquid or a vapor for any.
What? Which is this you're asking?
So my screen is visible.
No, you're asking
Hello.
something of today's whatever we have done or something else.
Hello.
Yeah, Sachin, you're audible.
And sir, my screen is visible.
Yes, yes, I can see your screen. No, I'm asking question. Which question you're asking? The thing which we discussed
Yes,
today
sir.
or
This one.
something else?
No, something else from assignment. This is seventh question. What is vapor or liquid flow ratio?
See, I think they are asking just the ratio of liquid and vapor. I don't know because I haven't seen your question. They are asking just the ratio of vapor to liquid. That's all.
Should I just ratio them and then answer
Guess
over
that's
here?
the
Huh?
guess that's the thing which they are asking. I'm just guessing because I didn't
Oh,
see the question.
yeah, sure.
Yeah.
Thanks.
Okay. Any other questions?
No.
Okay, fine. Sanjay. Okay. So in case if you don't have, can we stop this lecture today and come back the coming week? We'll solve the distillation thing next week. Okay. Okay. Then in that case, have a good week. See you then. Bye.